Cool. So I went ahead and put a little review here, a refresher for last class, and we never finished fully talking about kernels. So I kind of want to emphasize a little bit more about the kernel trick and the kernel functions, and then we can jump into the code. And I got a VM up and running with support vector machine code on there, so we'll get to it. Don't you worry. Okay, so first things first. Remember, unlike linear regression and other machine learning algorithms, support vector machines expect things to be linearly separable. We talked about the kernel trick as a way to increase the dimensionality so that that hyperplane is still in a way linearly separable, but it still has to be something in the form of a straight line or made up of straight lines. Like a plane is basically a bunch of straight lines together, right? There's no curves or anything like that. So of course, support vector machines work great with something in 2D that's linearly separable, but so would linear regression in the basic sense, right? Really, the big advantage of support vector machines are going to be when we go ahead and use it for linearly separable data using the kernel trick. But just as a review of something that is linearly separable, we have our example from last class where we have two classes because SVMs are very good with binary classification. We got the circles and the X's, and the example we worked in before, like Democrat, Republican kind of thing, and we're trying to separate them and separate them based on the features, and the features are of course considered as a vector. So each of these could be a vector that is not necessarily one-dimensional. It could be any dimensional, p-dimensional vector. And so because of that, the points that are actually on the hyperplane here, we like to call those the support vectors because those are the ones that are deciding where the boundaries are. We could just as well move these things back like that, and they're not going to change where the margins are. The ones that would change it would be if we went ahead and moved this back. Then the whole boundary would move with them up until there, at which point this will become part of the boundary as well, okay? So that's how it would work with what are the support vectors, which is where the support vector machine name comes from, okay? The support vectors on the bottom there are the three X's that are in the line. Yet again, if these guys on the back move, they can move all they want. They can move all the way over there. Still not gonna change the boundaries there, the margins. What's really gonna change, to make sure we define, these are the margins, and this is the boundary per se, okay, the center one. So H1 and H2 are your little hyperplane margins. And so I give the example of like war, they're holding the front, World War I, that's the front. And the backup soldiers, they're there, and if the front breaks, then they're gonna become the new front, right? So like if these guys disappeared, they're taken out by the enemy, then the new front is going to be that right there. That's gonna be the new front, right? So ultimately, support vectors are the ones that define this margin. And of course, the problem that we're working with is trying to maximize that margin, right? We're to optimize it, trying to make it as big as wide as possible. And that's pretty much what we talked about last time with that. What you're seeing there is not what I'm seeing here. That is weird. Like, I'm not seeing those dots. What happens if I try to erase them? And I can even erase them. That is weird. Let me try to exit out of that and back in. Okay, there we go. So some weird latency issue going on there. Okay. So that's what we talked about last time, and again, that optimization problem is not an easy thing. There's some hard math involved and so on. Okay? I am using what they told me to use, which is Notability. So yes. Okay. Then we got linearly separable data. Okay, that's what we've been working on. That's what this is. But then we get something like this, right? And that's the problem. That is not something that is linearly separable. I cannot come up with a line that could separate that data without errors. Like there's no line. I could draw lines all day I want, and I'm never going to be able to separate those two classes, right? Of course, we as humans could see that like, well, we could draw some kind of circle and call it a day. But you cannot do something non-linear with SVMs. That's where the kernel trick comes in. So what I went ahead and did is I went ahead and actually worked out a numerical example to show you a very, very, very bare bones and simple kernel trick, so that you don't just think of kernel trick as magic. okay? That just makes things in higher dimensions and separates things. I wanted to show you something real. And so I took the painstaking time of actually plotting points and figuring things out. And so here I have an example with actual values, which kind of represents this in a way, of the two classes. We got the blues and the reds. And yet again, you know, we're saying like Democrat and Republican or whatever, or what could be the other thing, British versus American, I don't know. Whatever it is, right? We're trying to separate the two classes. And as it is now, yet again, there's no way you can draw a line, a straight line, that can separate the data without errors. I could try putting something here, you know, and, you know, I'm not getting that many errors on the blue side, but I'm getting, you know, and on the red side, I got everything good, but these are going to be my errors here. These are going to be my 3 errors potentially, right? There's nothing else that I can do here. That's it. So I am forced to use something nonlinear, or I can use my kernel trick to increase the dimension of the data, just like I showed you in VR last time, to do that. So how do I actually do that? How do I realistically do that? Okay, well, notice that if we go ahead and create a third dimension, and we can do whatever we want with that dimension, it is our world, we can define what that dimension is going to represent and how it's going to be represented. And so we're going to say that the z dimension, which is going to be the depth, or in this case, it's kind of going to come out of the screen at me here. So it's going to be like looking up. And of course, if I had VR, that'd be easier to show you, but you know, that was last class. And so that is going to, we're going to use that to be able to make a plane between two things. So if I have, you know, this is one class and that's the other class, we want to separate them. So right now everything is flat. We want to give that height and we can put that plane in between, okay? So that's kind of what we're trying to do. And so what I'm going to pick for that dimension is going to be x squared plus y squared is going to be my z. And notice that that's not something I pick randomly. That's actually the equation for a circle. And why? Because that means that anything closer to the point 0, 0, that's going to be kind of like the center of the circle, you can think of as a radius coming out of that, which means that all these 3 are going to be closer in that z-axis to 0. These are going to be a little bit further away, those 2. And then everything else in blue is going to be way, way further away than anything in red, because it's further away from. So in reality, that z dimension is really representing the distance from the center, okay? And I intentionally did that because I think that's something that in my data, I can easily see that if I draw a circle there, I would be able to separate the data, right? I can see that. I'll actually leave that circle in there. No, because it's kind of crossing things out. So yeah, okay. And so once I decide that that's going to be my z dimension, I can go ahead and compute the values of the z dimension, okay? Now you're not going to always want to do this. We'll get to that in a second, as I said. But suppose you were just doing it this way, okay? The simple way. So you compute those z values. So how do you actually do that? You just plug it in. Here I went ahead and picked 4 points out of the total, what is it, like 2, 4, 6, 8, 10, 12, 13 points. And so I just picked 4 at random just to show you what to do, okay? So what you do is you take your x and your y and you square them, since that's what we picked, and then you add them together. So 0 squared is 0, and then negative 5 squared is 25. So that gives us 25. 5 squared plus 5 squared is 25 plus 25 is 50, and so on. So that's pretty much how I got these values. This means that this is now going to be my z values for those given points, okay? So I went ahead, and just to show you how it would look like, I went ahead and plotted it again, okay? So this is me going ahead and putting in the 25, the 50, the 8, and the other 8 into the coordinate system that now includes that third dimension. Okay, so here we have our third dimension here and what those points are going to look like. You would do this technically for all points that I have, but I just did it for 4. No point in doing the same thing repeatedly. Okay, and so before I show you what that's going to look like, I wanted to kind of show you that what I'm going to be drawing and how I'm going to show it to you. So if we look at our XYZ space now, it's going to look like this. You know, before we were dealing with just this front plane, right? That's really what we were looking at in this graph, that front view. But now that we've added that depth here, that dimension, which is really, that dimension is based on how far away you are from the 0, 0 coordinate, things will look a little bit different. So rather than me drawing this same X and Y axis, because it's just going to be the same thing, it's pointless, I'm going to go ahead, which is what it would look like, is I'm going to look at a top view of that. And so that means I'm going to look at the X-axis and the Z-axis and ignore the Y-axis for a minute. Now, why am I doing this? Because I don't want to have to draw a 3D picture by hand, okay? But ideally, you would be doing this actually as a 3D picture. But again, in VR, easy to do. Here, not so easy. So just to show you representing it, I'm showing you a top view, okay? That's all I'm showing you, because I don't feel like drawing a 3D picture. That's way too hard to do. That's not in VR. You can actually walk around it. And so if I do that, this is exactly what I get, and this is accurate, because I mean, you know, to an extent of me by eyeing it out, but it's to scale and everything. Okay, I went ahead and compressed the scale so that each line is increments of 2 versus increments of 1. I did have to do that because otherwise, you can see already that this is pretty big. It would have been twice as long, which would not have fit on the screen here. And so as you can see, now the data is very linearly separable because we have all our blues up here and we have all our reds down here. And some of them are stacked because remember, we're looking at this from a top view. So here, there's actually 2 reds. They're just stacked on each other, but we can't see them because we're looking at them top down. If we peeked on the side, we'd be able to see them just like I was showing you on VR the other day. Same with here with these 2, okay? But other than that, that's very good for us because now this is very, very linearly separable. And as you can see there, I went ahead and kind of eyed it out what I think the ideal margin would be for this data. Of course, in reality, you would take into consideration not just the X and Z axis when making this margin, but you want to take into consideration all 3 axes, right? X, Y, and Z. But ultimately, I do believe that it would look like this. That boundary plane that you would be making and the support vectors for it would look like this, at least from the top view, okay? And so, as you can see, we have 3 support vectors. We have 2 red and 1 blue. And those are really what's holding it from making the margin even wider. And then we have in our center our little hard boundary, okay? And the other ones are like the soft boundaries per se. And so now we've gone ahead and had data that was not linearly separable, and we in two dimensions here, and we went ahead and upped it 1 dimension higher, and using our little kernel trick, which was essentially x squared plus y squared is equal to z, we went ahead and made it linearly separable, okay? So there is an actual practical example with numbers for you guys to feel better about. But that's not enough. That's not enough. And here, actually, I did try my best to draw it in 3D. Although in this case, I flipped it a little bit. So we're no longer looking at it in a top view, because this picture here is a top view, but now the top view is technically looking at it this way. So I kind of flip things a little bit around, but it's still the same graph, just looked at it from a different angle. That's why you can see the Z is like that and the Y is like that, going like far back, right? And so here you can kind of see how the data looks like. There's a circle here and an outer circle, and then there's a space in between them, and that's where our hyperplane is separating the data linearly, okay? So never any curves, parabolas, or anything. It's always going to be a hyperplane. So SVMs have to always be linearly separable. And if they're not, we're using the kernel trick to make them linearly separable, to make the data linearly separable. We're still not making an SVM that is not using linear. That's different than other algorithms where you're actually trying to implement a curve or things like that, okay? So how do we feel, chat? We still here? Still alive? Everybody's very, very quiet. Hopefully not scared. How are we feeling, chat? Yes. Okay, we got somebody that's alive. That's good. I'm glad. I think seeing an actual numerical example helps. Okay, let's take this a step further. If you remember last time, I was talking a little bit, and I know it was kind of, I do say VR would have been nicer, that there is a computational thing. It's hard to visualize a top-down view in 2D. It is, which is why I kind of try to draw this square, and really we are looking at we're looking at this here, and that's what this looks like there. You know, if I had this in a piece of paper, then I could show you that. You know, this the tablet. No, you can't see that. So, but you just have to think in higher dimension. So like here we have a paper, and so this paper, you can imagine that T sign like that, and so in fact maybe I can just get some scratch paper, and that's okay. And you can kind of flip it like that, and you're looking at a top view, and then the original graph was just looking at it coming this way, okay? But still, you would be looking at it like a 3D space. But I'm just saying, when you're trying to explain to someone, and when you're trying to draw and represent something, or try to see a pattern, it's so much easier to just draw a two-dimensional picture and just do a bunch of them. Kind of how if you were developing and you're trying to create a texture or a shader for something, and you would do the different sides of it separately. It's a little bit hard to conceptualize, I know, which is why I try to do my best to show you both 2D views and then the 3D view. The 3D view, of course, is way less accurate. I just put dots, and there's more dots in this than there's actually dots in the actual example, just to show you, right? This is far more accurate and supposedly clearer, but it is what it is. We make do with what we can. Okay, now let's go a step further here. I was mentioning this, and I might have mentioned it kind of briefly because of the time constraints, that computing this extra dimension is computationally expensive, okay? Especially because you have to when you're creating that, when you're trying to optimize that hyperplane, you're trying to find the farthest away distance that you can put it at. So there's a lot of computation you have to do. And the more dimensions that you add, it's the more computation you have to do. And that's really bad because, with machine learning, you're typically running these things like for hours or days with multiple iterations and epochs and trying to converge and trying to find that optimum. We're talking about that parabolic optimum because it's a quadratic problem at the end of the day. And so, we even said like we were trying to use Lagrangian and other things like that. And so that's a lot of math involved. And so that extra dimension adds a lot of math. And it might not just be one dimension. You might go to some 20th dimension to actually be able to linearly separate the data. It might be up to that. In fact, you could run into a problem of overfitting if you go too many dimensions high. Let's put it to you that way. Okay, because you could actually say that each dot is its own dimension, and do something fancy like that, but you're overfitting at that point. So the point is, you can get pretty high in the dimensions. And so because of that, you don't just want to flat out compute the Z, or in this case, how many Z's you have, you will probably run out of letters, dimensions, okay? And so ultimately, because all you're really trying to find to be able to measure how far away something is from the other is the dot product. If you remember dot product, two vectors, that's the middle one per se. And the dot product, I actually have a definition here. The dot product between two vectors is the sum of the products of the corresponding components, okay? And so that's really what you're trying to find. So rather than trying to create the dimension first and then find the dot product, skip creating the dimension and just find the dot product of the hypothetical dimension that you're making, or dimensions if you're doing multiple ones. And so that's really kind of what I'm trying to say here, that all we really need is the dimension, is the dot product for the dimension. So if you think of a dot product of something that has just one dimension, it's just that, multiplying those two components. Not multiplying, but doing the product of them. If you're looking at something that's two-dimensional, then you do you do the product of each of the separate ones and you add them together. For 3 dimensions, so in our case, Z dimension we're adding, you would be adding this extra workload to do, right? Here's the thing. You don't just compute that. You don't have to compute that because, again, you just need to compute the result so you can use that as your kernel function. So really, in our case, we're dealing with this one, but really we can simplify that by plugging in what Z represents. And then we never ever have to compute Z separately. We can just do it manually there, and we can use dynamic programming and things like that to not recompute things. And we can use that as our kernel function. Now you're looking at that and saying, well, we're still sort of computing Z, we're just not calling it Z. Yes, but we are saving some work by doing it in that format versus the top one. And by work, I'm saying computational work. So you do want to save some computational work with kernel functions. You don't just want to increase the dimensionality and call it a day. Okay? So I just wanted to touch on that. And as I said, there's a couple of kernels. There's RDF, radial basis expansion or function. There's polynomial kernels. This would be kind of like a polynomial kernel. there's linear kernels, and there's a bunch of other kernels, but I'll show you a little bit more once I show you some of the coding. So let's go ahead and actually see some code now, shall we? So let me go ahead and switch over. Not Valorant. Where is the VMware? Here we go. And I went ahead and actually, it zoomed in, so you're only seeing part of my screen now, because I think that way you can read it. So my question to you is, can you read that size of font? And I hope the answer is yes. But I want to check. Can you read that? Make sure you're watching in 720p or higher definition. So, okay, yes, great, perfect, awesome. All right, awesome. Okay, so I'm gonna go ahead and show you some stuff, but actually, sorry, jumping back and forth, but I wanna first just show you really fast the website. So let me, that's funny. So that's actually the size of the thing, so you can see that. I'm gonna actually open in the VM, the browser, because I want to show you the, so we're gonna show you two libraries. I'm gonna show you LIBSVM, which is the real OG library for support vector machines. And then I'm gonna show you the Scikit-Learn version of that, which actually is using LIBSVM just repackaged, because Scikit-Learn is the noob-friendly machine learning way to do things. And so, I mean, there's nothing wrong with that. Okay, so this is the official LIBSVM website, and I believe this is a link to their paper or their like research homepage. So really, really cool people. They got a bunch of projects going on. They have more than just support vector machines. You can see here all the different things that they're doing. And so really the one that we cared about is LIBSVM, okay? And then the other one that I'm going to actually jot down here is going to be the Scikit-Learn page. And these are the two pages that you want to be familiarized with when it comes to support vector machines. And I'm about to post a link on Twitch for both of them so that you can go to them as well, if you would prefer. I didn't copy and paste the second one. Hold on, posted the same link twice. There we go. Links have been posted now, okay? And so, if not, you can just see it here. Let's talk about LIBSVM first, since there's the OG people. Okay, so there's the name of the guys that made them, and as you can see, it is continuously being updated. In fact, I bet the version I have is out of date, because the code that I'm showing you is code that I worked on before July of last year. And so it says here that the latest version was from September 11, 2019. So my code is out of date already. That's an entirely different topic about reproducible research that is very, very valuable. But, you know, different topic. So they have a nice guide now that they made called Practical Guide for SVMs Classification, where they actually walk you through a bunch of things. I recommend that you check it out. The only thing I want to show you from this right now is this is the math per se of the kernel function. So you can see the typical kernel function thing you do is you do the k, xi, xj. And so you're saying, what is that going to be done? So for example, for linear, all they're doing is a transpose. And they're taking those together, right? For polynomial, which is more of what I was just showing you, is there's some exponents involved in that. Radial basis function, that's a little bit tricky, so I'm gonna hand wave that. And sigmoid, you've probably seen with neural networks or other things like that. Okay, and they give out some examples, and then they talk about some basic procedure on how to do it, and ultimately, you know, I think it's a bad approach to machine learning to do this part. But honestly, it's the best thing to do if you don't want to go too in depth with the different kernel types, which is try different kernels and see which one actually gets better results. What that's really saying is try jumping into different dimensions and see which one actually separates the data better. That's kind of what's happening there. But even within like polynomial, you can pick different values which will completely change how the data is handled. So even within the kernel, you can modify things to get completely different results, really. And I'll show you that in a second. I have an experiment that I ran personally, and I got completely different results by just tweaking single values. So There's a lot to be experimented with there. There you can read that for Rbf kernels. So the best kernels, people say Rbf is one of the best ones. I personally use polynomial, but people say Rbf will get a little better results. I think linear one is the one that's the weaker one, but some things linear is good for. That's the other part. Certain kernels work good for certain problems. The best way to pick a kernel is to do research, read some papers, and see what historically has worked for that kind of problem. That's going to kind of give you a starting point on which kernel you should use, unless you want to do the hard math and see what's better. Obviously, the example I showed you, that baby example, you could see that some kind of kernel that made a circle, like a circle formula, worked because you could see that visually in your data, like, oh, okay, this is just a circle. That's not always the case. Those are baby examples to show you basic concepts. In the real world, you don't see that kind of stuff. It's not that trivial that you can just like see it and no. There are a lot of cases where like you will see data and you are like, I have no idea if the data is even representing multiple classes. Like this just looks like a blob of data, and the computer somehow manages to do it. And that's why sometimes like deep learning and things like that, you're like, whoa, how does this even work? Like I don't even know what's happening. Yes, that's kind of what the real world looks like. So it's not as easy to pick a kernel as us being like, oh yeah, we can just kind of make our dimension be how far away things are from zero. Not always the case. So anything else that I want to show from here? That's just talking about, this is all really useful to read, to be honest. So I'm just going to go ahead and skip that because you can look at that on your own. And I'm going to go back to the guide here. What I really want to talk about is down here, this. And I might zoom in a little bit more on this. So when you're running LIBSVM and you're running your kernels and you're running your support vector machine, you're going to have to pick up a couple of settings. And I wanted to just give you an introduction into what some of those settings are. And you can go with the default. That default is actually really, really good. But if you want to try something else, you can. So for example, the most basic type is what kind of support vector machine you're running. Remember I talked about support vector clustering as a way of an alternate to k-mean clustering and unsupervised learning? You have some ability to do some of that there. Otherwise, then you can just stick to support vector machine, okay? So you can set what it is, and then you can set the kernel type as I was talking about here by simply putting a parameter. So when you're running this, it's command line arguments in a way. You're setting things of what you want. So kernel type here, for example, is 1. So they're going to run it with polynomial. If you're going to run it with radial basis function or sigmoid function, then you can do that. So you can pick whatever you want there. And even within there, as you can see, the degree matters for polynomial. That's a big thing actually with a degree. You can actually go in and change that. The degree by default is 3. You can go higher. The higher you go, you can think of that like going into higher dimension and for more fancy data. But if you go too high, you're going to probably do some overfitting or weird things are going to happen. So again, this is an experimental thing unless you want to do the hard math to prove that one way is better than the other one. And so those are going to be your big ones. You can mess with gamma and the coefficient stuff, but that's not going to be as big as the degree for polynomial or just picking the kernel function itself. Cache stuff and things like that are going to be just for efficiency purposes. You can Google on your own and like to increase the cache and things like that to hopefully run it faster. I have had things where like a support vector machine will converge and finish in 3 minutes versus like 24 hours. And they can go, I know people that can go way further than that, depending on the amount of data they have and how accurate they're trying to hit. So at that point, when you're dealing with something that's taking days to run, that's when you really want to go and tweak in here. Otherwise, you call it a day for a toy example when you're just experimenting. And so that's basically the main command line arguments about this that you want to know. And really, this is, if you know this, you're good to go. So let me actually show you now what it looks like in code. Okay, so this is a project that I did and for that actually I have, you can look at my dissertation, but ultimately I have it here. Give me 1 second. I moved the window and I can't move it away. There we go. I had data like this. Okay? So this data has 1, 2, 3, 4, 5, 6 columns. Okay? 5 of those columns are my features. That's my little vector. The last column is my y's. That's the class that something belongs to. So in this case, this was for error correction using for OCR, using the predecessor and successor word, and the weight, and other things. So for example, if I remember correctly, and I don't have to remember, I have it in my paper, but I would have to actually open in my paper and see. Aha, here we go. Okay, so the first one is the Liebenstein edit distance. The second one is the confusion weight, and I'll explain what this means. Then the unigram frequency, backwards bigram frequency, and forward bigram frequency, and the output of whether it is correct or not. Okay, so what that's saying is, let me jump back into the tablet. And the reason I'm explaining this is just to see what I'm actually trying to run a support vector machine on. So I have 5 numbers, and the first set of numbers was a 3, 37, 2, 0, 0, 0. Okay? And what this means is if I'm looking at the word register, okay? And the word register is misspelled. And even though I have an example there, yeah, let's copy that example then, because that one's actually more meaningful. So let me copy a different set of numbers. Otherwise you get confused and I will lose you. So that would be 3. Sorry. 1, 918, 83, 83, and 0. And 0. Okay, so that's 6 numbers as we have here. Yes, okay. What this means is we are looking at the word register. Okay? And that's our misspelling. And the correct word is actually register. Okay? And so we are looking at candidates to correct the word register into a correct word in English. And one of the candidates that we're looking at is register. Okay? We don't know if that's actually the correct word, although I told you it is, but we don't know. However, we want to know if that's a good idea. Other suggestions is, for example, the one that I showed you before, the one that had the 3, the 37, the 2, and then 0, 0, 0. That was a suggestion for the word existed, okay? And as you can see, just off the top of the back, if I hadn't shown you what the right word was, you would probably say that that's a way better candidate than existed, right? And one of the ways that you would say that is based on the similarities of the words. And when you're talking about the similarity, you're talking about the edit distance in Liebenstein or Jacquard in the sense of how similar the word is, what kind of modifications do you have to do to one word to make the other one in terms of insertions, substitutions, or deletions. So in this case, we only have to do one substitution, and that is to substitute the word H for an R. And you can very likely see how with OCR, which is optical character recognition, which is like scanning a picture and then converting it into text, you can see how a scanner may have confused the letter H for the letter R, right? There's an H and there's an R. And let's say that there's some dirt here, it's already going to try to assume that it's probably an H. So it's a very, very likely kind of typo that you see very popular, right? You're not going to see in OCR, for example, an S being misrecognized as a W, but you might see that in normal spelling correction because the keyboard is ASWD, right? Or sorry, no, key WE and then ASD, right? And so these keys are very close to each other, and so it's very likely that people may actually misclick. But the kind of errors that you see in OCR are different than that. They're going to be based on visually similar looking letters. Okay, so this number represents that edit distance. So because we only have to change one letter to get from register to register, we have a 1 there. On the top over here, we have a 3 because we would have to change 3 things in here to convert it to that. Now, I believe you would have to change the H to nothing. So you delete the H. You would have to change the G to an X, and then the R to a D. And there you go. Those are your 3 edit distances that can get the word register to existed. Okay? So that's going to be basically what that first column is. And that's a feature that I'm using because I want to say that probably the smaller that number is, the higher the likeliness that this is the correct candidate. Okay? But I want to go further than that because it's not always going to be as clean cut as that. Okay? There might be other situations where a higher Liebenstein edit distance may be the correct answer. Ideally, you know, with OCR stuff, you see 1 error per letter, or sorry, per word, not that much, right? But it is possible. So the other things that I'm looking at is context-based, and also looking at the likeliness of letter substitutions, right? Which is what I'm talking about. So this H to R situation, you know, if I know that this is a very common thing, then I want to give an increased sort of importance to that type of error because I'm like, yeah, it's a very common error to go from H to R or vice versa. And so we like to call that the confusion weight. Don't confuse this with the confusion matrix of like true positive, false positive, true negative, and false negative. Okay? Oh, and yet I said I would look at Discord, but I haven't. So now I'm looking at Discord. How are the z coordinates being calculated for the xy pairs? I use x squared plus y squared. If it's the distance from the center, should it be square root? I can make my z dimension whatever I want, and so that's what I picked. So it doesn't necessarily have to be fully the distance, but I could have done square root. I just chose not to, but I could have done, and I think that would have worked as well. Except it would have squished the height of that smaller. So it would have squished this smaller here, but it would have still worked if I used square root. But by not using the square root, I make it a little bit bigger so I can see that as and I like things being a little bit bigger because I can make that margin artificially bigger. So that's why I didn't take the square root. But yes, I could have done the square root. So there is the answer to your question in a slightly delayed fashion. Okay? I'll try to keep track of Discord. Okay, so all right. Back to this. So that second number is the confusion weight. That is going to be how often do I see an H being misread or an R being misread as an H, okay? And as you can see, that's a very common error that I have seen with my training data. And that is 918 times I've seen it. So that means that compared to this one up here, how often I've seen those kind of substitutions, you can see that it is more common to see the register error than something from like existed, okay? So that's why that number is bigger. And then this number here, the 83, that is going to be my frequency of the unigram. So how often do I see the word register in my solutions? Like how often do I see that as a word actually in text? So typically, I'm not going to see misspelled words that often in text. I'm going to be seeing correctly spelled words in text, and if I'm talking about computer science, then I'm going to be probably seeing a lot of the word computer in there. So that's going to be a very high frequency word. So if I'm trying to correct something that looks like computer but it's misspelled, more than likely I'm trying to talk about computers versus like commuters, right? That's not something related to computer science often. You may see it in text like somebody is commuting to their computer science class, but it's a very rare thing. So I'm trying to give more weight to something that's more frequently used. So that's what the unigram frequency is. As you can see, I don't really use the word existed a lot in the text that I have, but I do use the word register. And that just happened to be in the text that I was working with for this problem, okay? Then the next things that we have are going to be the backwards and forwards frequency. What that means is that I'm looking at context at this point. The word before and the word after. I look at the word before, and whatever that word is, how often do I see it happen before this word? And then same for the one after. And as you can see, I do often barely see the word before this, which I believe is the word da. I didn't write it down, but it's the word da. I see the word da very, very often before register. And so if I see the word the register, then I'm like, well, I've seen a lot of the register. And if I see the register, that gives me even more reason to believe that I should replace register with, or replace register with register, right? whereas I've never ever see existed, and therefore I never ever see something before existed either. That's why that's 0. And same with forward and backwards, just the same thing, okay? So anyways, that gives you a sort of an idea of what this data set represents. And this last value, the 0 at the end, is going to be the whether or not is the correct candidate, okay? So actually the second one, this one should be a 1 because this is the correct candidate for this word, okay? And so if we go back now to the code, you can see that this second column here was the one that I was working with, okay, and the first one, okay? And you can see that that's a 1. And I want you to notice something that I run into as a problem, which I don't think I'm going to get to, but I can very briefly talk at the end, and that's balancing your classes. You can see that this is a very unbalanced data set. There's a lot of incorrect candidates that are being suggested, and very few correct candidates, right? We only got of this sample of data that I am showing you, because the data is a lot more than this, of course. I can't remember off the top of my head the number of data, but I could try to open it or just see the size of the file. But it's a lot of points, right? Each of these can be a training or test set, right? I'm going to do my split by doing 20/80, but you can do whatever you want. But the point is that I have a lot of these individual entries, right? And so as you can see in this sample of the 2, 4, 6, 8, 9, only 2 of them are correct candidates that are being suggested, and 7 of them are incorrect. And actually, this is a very, very generous version of that. In the real one, there's more like 20 wrong and 1 correct. This biases it actually causes a problem with training, because your model will get used to just saying no to everything, because it's very rare that he gets something suggested correctly. So he just gets super picky and just refuses everything. That creates a problem. So to fix that, you have to balance your data set, and you can use things like smoke. But like I said, hopefully in the end I can talk about that. If not, that you can check it out on your own time or read it on my dissertation or on the internet. So, okay. So now we know what the data set is. Now I'm going to show you how we're going to put this in Python, and we're going to be able to run it with either LIBSVM or Scikit-Learn, okay? So here we have the LIBSVM version. Perfect. So I normalized my data in some of the and some of the experiments I did, I didn't, and in some of them I did. I highly recommend, this is a basic 101 machine learning thing. You should normalize your data for certain machine learning algorithms, support vector machines being a big one of them, because that will make it converge way faster. Like we're talking like non-normalized version of this was taking hours, and normalized one took minutes. Will oversampling work for this data set to balance out the classes? Okay, so oversampling depends on what you define as oversampling. Are you generating samples by extrapolating data? If so, then yes, that is one way to balance things out. But oversampling, if you're trying to get more data from your input, that's great if you have it. What if you don't have anything? If you don't have anything to get anything from, you can't. But what you can do is you can extrapolate data to create more data, which is what Smoke will do. You can also just completely delete samples from the heavy class, like the one that has a lot of. Of course, we don't like doing that because we're losing data, and so we have less data to train on. So you do want to extrapolate your data to create more data, and that's what Smoke and other things do. So yes. Okay. So I have a normalized version, and as you can see, I have commented out other versions that are not normalized. But I normalized and gave us the best one. Where can I read the dissertation? I posted it before. You can literally Google it, and if not, I'll post it again at the end of the chat. It's also on Discord. But if you just Google, again, I forgot the name of the dissertation, OCR post-processing using machine learning tools, and you Google my name, then it should come up on UNLV Digital Scholar. And if not, then just let me know, and I'll send you a link. But it is, you literally just Google my name, and then Google Scholar, and you can see a list of papers, and you just look for the one that says OCR post-processing using machine learning tools. And there's a lot of the stuff that I've been using for the PowerPoints today or presentations came straight from that. In fact, I didn't remember some of it. I actually had to read my own thing to refresh my mind, and some of it didn't even come back then. So sad. Okay, so here we got just opening a file at this point. Opening the file in read-only mode. that is going to load basically the data, but we haven't loaded it yet. Okay, basic Python 101. This is maybe not the best way. Go ahead and ask Eric for the best way for this line comprehension stuff. You know, if he's not too busy, he can probably show you some nicer and cleaner ways of doing this. This is a nice and dirty way. You just call it a day, slap it, and be like, this baby can handle any data you give it. Okay, so I can talk crap about Eric because he's too old to use Twitch. So yeah, okay. So you can defend yourself in Discord, Eric. The next line we're going to see is we're going to be reading each line of the input data. So remember, our input data is literally what I showed you. So it's actually hidden now because I put it behind this. So give me a second to pull it back up. But it's this, okay? It's just a bigger data set than this. But you can see I cleanly organize things like one per line, comma separated, okay? He says he hates me sometimes. That's right. He hates me sometimes, but he likes me the rest of the time. So that's okay. All right. So, okay. I'm just copying Tagua, you know. Tagua makes fun of him all the time, so I have to make fun of him all the time, you know. He has to feel welcome in the class. So, okay. So here we got our row that we're creating, and we're going to, as you see, everything is comma separated. So we're going to split it by each value. So we're just splitting it by value so that we can create this sort of 2D array per se, even though it's a list in Python that has the data. Okay, so that's what I'm doing here is I'm doing a for loop and I'm splitting the data so that it is read in, and the read in is a floating point because when you normalize, if you remember what normalizing is, you make the data go. There's different ways of normalizing. There's standard deviation and there's just basic min max. Min max saying you go from 0 to 1, I believe, or 1 to -1. Ooh, snap. Which one is it? 0 to -1 or 1 to -1? I can just open the normalized data and see myself. Let's see, how big is that? It's 22 megabytes, so I don't want to kill my computer, so we're gonna open just a piece of it. So more norm regression matrix. As you can see, it looks nasty. There we go. That looks much better now. Okay, so it's going from 0 to 1 potentially. You can't see the edge. Now you can. See? So this is what the real data set looks like. As you can see, it's just a bunch of numbers from 0 to 1. And they're big numbers. You know, this is a really tiny number. That's why it says that -5. So it's actually, so even though it looks like 8, it's still actually between 0 and 1. It's actually 0.0000891. Okay, so they're still between 0 and 1. So just because it looks like an 8 there, you got to remember your scientific notation from math classes or physics classes, actually. And so, yeah, that's what the real data looks like for normalized, okay? Normalizing is just basic math to convert things from 0 to 1. Trivial function, I have it in my dissertation. That's it. I don't want to go too off topic or we'll run out of hand with that, okay? But anyways, that's why we're putting it in the floating value. And floating value in Python is basically a double in C++, which means we have as much accuracy as we can achieve, okay? So then I split it here for tagging purposes so that I could remember that this is the distance, the weight, frequencies and stuff, but I don't actually use this splitting. So it's just there, so don't ignore that line, a couple of those lines. This is like working code. This is stuff that I did that worked, and then I moved on with my life. So I never try to clean it up and make it amazing, but it is documented. See, nicely documented code. My 302 students that are watching this, take note that I do document code. I don't just preach it. Okay, so yeah. All right, and so what I'm gonna do now is I'm gonna do my splitting. With machine learning, you always wanna split your data into training and testing, right? And ideally, you actually wanna do a three-way split. You wanna do training, test, and validation, right? And you don't wanna touch that validation data set until you're done with the experiment. In my case, I was never done to the point where I wanted to just validate and do and call it a day, right? Because this is an ongoing process. I'm still doing things to this, even though I haven't in a year, but I will come back to it at some point. But that's the point. So if you were to actually like try to defend and say that your combination of this SVM with your machine learning algorithm is the best, you would want to do cross-validation tenfold, or you would want to do some sort of validation at least. So then you would split your data maybe like 70%, 20%, and then 10%. And that last 10% is validation, which means you only run it once. And this is the problem with papers. I don't want to go too off topic, but a lot of the times, they lie. They say, oh yeah, our project, like when we done validation, achieved like 99.9% accuracy. That's a lie. What they did is they ran the project on the training set, then on the test set, and when they were happy with the tweaks, they ran in the validation set and then they got like 5% accuracy. And then what did they do? They actually went back and tweaked it to increase the validation result when they shouldn't do that. At the point that you run the validation, you're supposed to stop working at that point and publish your data, or not publish it, but at that point you're supposed to stop. What you can't do is you cannot finesse your output by changing what your validation is. Once you run your validation, that's like a one-way road. You cannot go back. But people do that all the time. That's why, take everything with a grain of salt when people say, oh yeah, we achieved this good accuracy, because a lot of the times it is BS. Okay? All right. Tiny spiel on that. Very passionate about that. Okay. So anyways, in our case, we're going to do 80%, 20% training tests. I have done other splits before, but that's the most popular one, and that's the one that I'm showing you right now. Okay. So what I'm doing now is I'm just creating two lists where I have that. Why I'm splitting into two lists is so that I can very easily run the model training on the training data and then run the prediction on the test data so that I can find my accuracy. And I keep saying accuracy, but I'm really talking about precision and recall, confusion matrix, true false, true positives, the whole 9 yards. Okay? This is the cool part. Look how easy it is to run the support vector machine on this with LIBSVM. Okay? I'm gonna go ahead, and I literally even wrote it here as a comment. This is from the README file. Okay? I'm not reinventing the wheel here. I'm literally just using the README file as an example and then just tweaking that, and I was able to get this running. Okay? We have a question. Doesn't it mean that validation set and test set comes from different distributions? Okay, so very, very good point. What you really need to do to avoid bias is you don't want to just split the data as cleanly as I did here. You want to randomize the data so that your test set contains everything from everywhere in the data, and so does your training set, and so does your validation set. Otherwise, you're biasing it in a way. So you're correct in that sense. And I did have some version of this that actually randomized it, but I didn't want to throw that in here because now it makes it more code, more complicated stuff. As you can see, these are versions. We have V and V2 and so on. So there's like V5. So yeah, okay. But yes, you are very correct in that, and I'm glad you brought that up because it's very important to avoid bias. Okay, so again, this is straight from the README. This is all you're going to do is you are going to call SV problem, and you're going to feed it the range of data that you want to do for your training and for your test. So first you're going to feed it your training. So in my case, I'm feeding it from 0 to training instances. So whatever that number is. So 120, it means you're feeding it 120 points, okay? So you're basically connecting your training data set with the problem. And also you're splitting it by feeding it the vector and then the class it's expected. So remember, you have two things. You have your vector, your x's, and then you have your y, which is the predicted class that you're trying to train it with. So you're saying, you're giving it your 1, 918, 83, 83, 0. You're giving those numbers which represent the features, and then you're giving it the 1 at the end, which represents that it's an acceptable candidate. You're also giving it the 3, 37, 0, 0, which are your features, and then you're giving it the 0, which means that it's not an acceptable candidate. And that's why you see a comma here. I'm giving it the x's and then the output column as the y's. Okay, so technically giving it y and then x. Easy to do. No big problem here, okay? All right, this is now where you're gonna set all your command line arguments from that LIBSVM website that I was showing you. So I'm gonna pop that open again, just to refresh your mind, and it's this right here. You're gonna pick whatever arguments you wanna run it, which means you wanna pick the kernel that you're gonna run it with, you can pick the degree, or you can just run it with all the defaults. You can experiment with this, and you're going to eventually set up a set of parameters that you feel comfortable with running it, okay? And that's literally what I have here, a bunch of parameters that I feel comfortable with running the data with, okay? All these different parameters. The only one that I really want to talk about is the fact that I'm picking polynomial kernel. And I am putting here that I'm putting a C as 10 and degree as 3. So I'm pretty much running with the default here, okay? All right, now that you set your parameters, so you made it point your data to the SVM thing, so it knows where to look for your X and Y's. You set the parameters you want to run a support vector machine with. So that's 2 lines of code. Everything else ahead was just literally like preparing the data set for this. But everything else was just preparing it. But the machine learning part is literally like SVM problem, SVM parameter, and now we're going to run SVM train. And SVM train is super easy. You don't have to do anything. Just literally pass in the 2 parameters that you loaded, the prob and the parameter. Prob is passing in the data set, parameters are passing in what you want to run it as. And then you wait. Wait for quite a while, actually. What is rip? Did we lag out? Or just, or rip as in you're waiting? I'm scared. I thought, did I die? I know, I see good connection, so I think I'm okay. But yeah, okay. So you run it, okay? At 3:45 result comes out, lagged. Oh, okay. Yeah, so don't worry. I actually already ran it and have the results. So I'm not gonna try to run it live and then have this thing not converge in time before the class ends, okay? But yes, anyways. So you run it, and then it's going to create a model. And that model is in model. You can actually save that model to a file so you can run this again in the future. Or you can just test it at that point. So the next thing that I'm going to do is I'm going to use SVM Predict. And that function is what I'm going to use to feed my test part of the data set to test the accuracy of my model that I just created. Okay? And so here I have that. And so I'm feeding it from training instance. So this is that Python notation that Eric loves. And I'm feeding it from starting from the point of the, so it's called list comprehension, I believe. And so you're feeding it from the last training point all the way to the last point. And I'm feeding that into my model, and I'm gonna go ahead and test accuracy. And then basically the rest of the code down here is just to pull from the data the accuracy. So for example, I get p label, p acc, and p value, right? And so for example, if I want to test the true positives, I'm going to go ahead and compare what p label gets. So p label is going to be what each training instance is predicted as. So if I feed it a training instance, p label will have a 0 or a 1. And that represents whether it predicted it as true or false, I believe. So if it predicted it as true, it means it predicted it as class 1 per se, okay? And class 0 as false, which means acceptable candidate or rejected candidate, okay? So a true positive means that I was expecting in my output, I was expecting in my training output or test output to get a 1. And the p label returned a 1, which means that it actually correctly accepted a candidate. A false negative, on the other hand, or a true negative, let's look at true negative. That one is basically in the output, I expected to get a 0, and the p label returned a 0, okay? Now for the errors. The errors are going to be, for example, a false positive. A false positive is where in my output, I expected to get a 0, but the machine returned a true, which means it accepted a candidate that it shouldn't have. False negative is the other way around. I was expecting to accept a candidate, but the machine did not. It was lazy, or it was too conservative in accepting the candidate. Okay, so if I run this, and then I go ahead and print it out, I can compute my precision and recall, F-score, and so on. And so this is what I get from that. And these are all the experiments that I ran. So for example, here's I think the best one was 6 or 9. So let's look at 9. These are some the things up here are some settings that that the support back to machine came up with. Don't worry too much about it. But that's just internal stuff. The important thing to know here is how many iterations it took. It took 130,000 iterations. Time-wise, it took this was a really fast one. 393 seconds. That's fast. Just to compare, look at this one. It took almost 19,000 seconds. That's slow. In my summary one, I actually summarized some things, and I can see here this one took 6.55 minutes. That's the one that we're looking at. It then took 5.25 hours, 8.76 hours. So you can see there's a big variation even within the same settings. And all I changed in this case was actually the data. And that was with the normalization and balancing and things like that, okay? So as you can see here, within that experiment, we went ahead and had a bunch of true positives and a bunch of true negatives, but we did have a couple of false positives. Those are candidates that were accepted that shouldn't have been, and a bunch of more false negatives, meaning that this is telling me that my model is a little bit too conservative because it's rejecting a lot of words that it shouldn't have, but at the same time, that's helping it in the sense that it's not getting a lot of false positives, which means it's not accepting things that it shouldn't have, right? However, because of that, we are getting a pretty low recall. Of course, these numbers we can improve if we were to use the class balancing that I was talking about. But of course, this is just using the pure SVM, okay? So that's how you basically run a support vector machine with LIBSVM. I'm gonna go ahead and review the important parts. This, get your data in a list in Python where each column, each row is a specific point, and then you go ahead and you feed it into your SVM problem, store that in a variable, and then set up your parameters, and then literally train it, wait a couple of days, and then go ahead and run that to test the accuracy. Oh, sorry, there we go, to test the accuracy. Okay, so that's it. Easy, piece of cake running this. Those 3 lines of code. Take a screenshot, or I mean, it's gonna go on YouTube anyways. Again, if you read the README file, it has almost this code by exactly, and you can use that as a starting point. Okay. The hard part, I suppose, is if you're not familiar with Python, which you guys should all be, is actually preparing stuff ahead of time. Okay, I like this much better. However, Scikit-Learn also has the ability to do the same thing. And so now I'm going to show you how to do the exact same experiment using Scikit-Learn's libraries. And that's actually, it turns out that if you know how to do one algorithm in Scikit-Learn, you can do them all because they're all very much using the same function names and everything. All you're really changing is a setting, and like it runs a neural network versus like a linear regression or something. Like it's very, very easy. By the way, with Track SVM, I had to import this utility here. Track SVM, sorry. LibSVM is actually written in C, I think, but it works in many languages, not just Python. With Scikit-Learn, you gotta import like sklearn basically. And in this case, I left here the iris thing, but I don't actually use the iris dataset. I was using that as an example because the best way that you can pick up Scikit-Learn is by going to the website and Googling support vector machines. And if you go there, they actually talk about all the kernels and what they actually look like, which is really, really cool. You can see here better how the kernels like separate the data, and that looks pretty cool. That does not look linear to me, but that's because this is looking at it in a higher dimension where it is linear. So even though it doesn't look linear, it looks like curves and stuff. In a higher dimension, there's a hyperplane that's separating the data. There's no curves, it's a hyperplane. It just looks like this to us in our 2-dimensional picture. And as you can see here we have a very basic example of using a support vector machine using Scikit-Learn. And then they use multi-class classification and so on. Okay? And so let me actually show you practically for the same data set and everything how it would look like with Scikit-Learn. We got a few minutes left, so I'll jump right in. I have my same input file, the same exact input file. I'm going to read it in, except I'm using this read CSV thing. And then I am going to, well, I have the comments here. I just don't want to read the comments out loud. Put the original column name in a Python list. I'm just putting it in, I'm just kind of finessing the data to get it set up. Ultimately, though, you want to use NumPy when you, I mean, you want to use NumPy always. I should have used NumPy even in like LibSVM, but I didn't. But you want to use NumPy because it's better for storing and it's more accurate and everything. So ultimately, in this case, though, what I did is I went ahead and copied the NumPy array into I copied my data set into a NumPy array. Sorry, I was thinking of why I have the iris stuff. I think I might have been I was playing around from FatMath class. That's why I have that there, because I don't know where else it would have come from. So don't nobody copy this when you're trying to do your LibSVM homework or your SVM homework for FatMath class. But anyways, I go ahead and copy the data here, And actually, the really cool thing about Scikit-Learn is that, to your question about whether or not we should randomize the data, especially for validation, Scikit-Learn provides something very nice for that, and that's random state. You can randomize the data so that it is randomly, so that your training set and your test set are completely random, cherry picked from the data. So instead of chopping and getting like the first 100 elements for training, the next 20 for testing, and the next 10 for validation, it will instead take the whole data and pick out from everywhere pieces. We got some lag. Let's give it a second. Okay, I think we're back from the lag spike. I don't know what got cut off from that, but as I was saying, with Scikit-Learn, it has the random state, which allows you to instead of taking like your training data, test data, and validation data in an order like that, you can just take the whole data set and then chuck out the percentages that you need from everywhere that get the data in a randomized fashion. You're randomly picking the data for each of the training, test, and validation sets. Okay. However, because sometimes you want to be consistent in when you're using this, you want it to be random, but you want it to be always the same random. Okay. If that's the case, then you can use random state. And random state is like a seed in C++, where you pick 42 in this case, and that's going to go ahead and always give you the same random, which means that if your data set has 10 and it decided to pick 0.5 to be in your validation, it will always be in your validation. And that's useful because you don't want that to switch around the whole time. You want it to be consistent, right? And then you can test around with test and train, but it'll be consistently the same test and train data set. Later on, once you're happy, you can go ahead and make it completely random, but baby steps. So that's what that random state thing is coming from. But the same thing as before with SVM problem, this is really what this is doing, is splitting it, okay? And then just as before, I am going to go ahead and feed it all my parameters. And this is actually using, again, LIBSVM. So you'll see that it's the same parameters, just in a different order. But if you look at Scikit-Learn's documentation, it tells you it's LIBSVM. And so all the LIBSVM features are here. They're just different names. So again, you're picking the kernel, you're picking your degrees and things like that. You set that up. You go ahead and you load into xtrain, xtest. You split out your data as you should there, as I showed you. And then you can just go ahead and run it on fit. So you do fit, train, and test, or xtrain and ytrain, and that is actually running the machine learning. You're fitting the model there. Once the model is done, then you can test it using Rbf Predict, and you feed it your test data set, and you're done. That's literally it. This is literally 78 lines of code. And that's because like the first 60 lines of code is just getting the data in a NumPy array. The machine learning part is basically from line 60 to line 66, 6 lines of code, because the rest of that is just printing stuff out for metrics like output. So what does the output from this look like? The output from that looks like this. This is my model. And then here you can see precision and recall of this specific instance, and also the confusion matrix and the time. Pretty fast as well. This is comparable to what LIBSVM was. But on my own personal experimentation, I found that LIBSVM was a little bit faster, probably because of the overhead involved with Scikit-Learn, but it's very, very minimal. I would say if you just want to learn one machine learning style, Scikit-Learn's got you covered, because they always have the same system, like fit, predict, and all of that. All you got to change is the machine learning model, xtrain and ytrain, versus if you learn LIBSVM, it only works for SVMs. Okay, so that was my brief introduction into support vector machines and showing you actual coding. You should be able to jump right in, frankly, whether it's LIBSVM or Scikit-Learn, and run support vector machine in any of the data that you have.